Welcome back to another presentation with information and perspective you'll find nowhere else. The title of our video is Gut Permeability, the link between gut dysbiosis and systemic disease. So we're not just talking about the obvious conditions and diseases associated with dysbiosis, like diarrhea, constipation, SIBO, and IBD. We're talking about just about everything you could think of. About 2,500 years ago, Hippocrates stated that, quote, all disease begins in the gut. That's about right. In many of my videos, I make the case for just about every disease you can think of being linked to an unhealthy gut. The only true exception is for those poor children, and of course their parents as well, where the children die at young ages from cancer. These are tragic cases, of course, of a genetic inability to control unregulated protein expression. There is realistically nothing in conventional nor natural medicine for these children. But for the rest of us, much of our health, or lack thereof, can be traced to your microbiome, the foreign ecosystem inside of us, either living in harmony with it or driving disease. This foreign ecosystem is separated from us by a series of cells called intestinal epithelial cells. To put this into perspective, it's easiest to think about our skin. Epithelial cells line an organ and act as a protective barrier. If you had a significant break in your skin from some type of injury, would you go wallowing around in a puddle of muddy water? I suspect not. But you can't visibly see the break in the lining of your gut. The skin has its challenges, but nothing compared to the gut. For about 7 or 8 meters inside of you is the largest interface between what makes you, you, and the outside world. These cells have a lot of responsibilities and bump up against a tremendous number of bacteria. The Paneth cells, which are a type of gut epithelial cell, I mentioned in my Crohn's disease video. They play a role in antimicrobial defense. The goblet cells are another, which I mentioned in my ulcerative colitis video, and are responsible for mucin production. But when we talk about gut permeability, we're usually referring to the most abundant intestinal epithelial cells, the enterocytes in the small intestine and the colonocytes in the large, which are responsible for absorption. The bottom line is this. These cells have to somehow allow the right molecules into your body while keeping out would-be troublemakers of all types. They are held together by over 150 identified proteins to date. And to the left, you can see what they actually look like from this electron micrograph imaging. When you do things to drive an unhealthy microbiome, these bonds are compromised. And this is when those unseen bad actors from the muddy water can enter into your body through that cut of your skin. But get this, the majority of the immune system is not just under the skin. It's just on the other side of the cells that line the gut. Hundreds of millions of years of evolution have resulted in this ready immune response to the most likely route an invader will take. Now, nutrients are absorbed via what's called transcellular transport, or absorption, which is to say, through the absorptive cell. But we're talking about permeability here, which is paracellular. However, not all permeability is bad. For example, here we have a model of what is called the pore pathway. It allows, in a controlled manner, things like water and sodium to enter the body. And here, you can see how these are tiny molecules, as these authors state, less than 0.6 nanometers. However, below, we have the leak pathway. This is our first area of concern. Now here we see larger molecules entering the body, and as they state, up to 12.5 nanometers, or said another way, up to 20 times the size permitted by the pore pathway. What parts of bacteria are entering here? LPS, for example. And this can be beneficial in reverse. You see here that the arrows are pointed outward, away from the body and into the lumen of the gut. Our zonulin protein exists for a reason. Although this is a mouse model, the principle is the same. This permeability is designed to flush away the pathogen with diarrhea, a protective mechanism, although not clearly always successful. Now, we're concerned about leaky gut for sure, at least chronically. But we're really concerned about this, outright tissue destruction. Here we have significant inflammation with resultant cellular death, allowing all sorts of molecules, including whole bacteria, from the gut lumen into the body systemically. We would typically think of this in the context of Crohn's disease or ulcerative colitis, but this could easily be relevant for anyone. This is largely what we're picking up from the gut permeability testing. And speaking of that, we can measure gut permeability in various ways. Although each method has its imperfections, when taken across the board, the data builds a consistent picture. It's just like with fecal microbiome analyses. If you did one fecal analysis, the results would not be the same if you did 10,000. With a larger sample size, the data smooths out, and we get a nice picture. And that's what we're going to highlight in this video. Try to remember these following methods of measuring gut permeability, aka leaky gut, as best you can. There's zonulin, which is one of our proteins, which under inflammatory conditions separates the enterocytes. We can measure that in the plasma. We can also measure LPS, like the polysaccharide, which I mention all of the time. This is pro-inflammatory and can work its way practically anywhere in the body and drive an inflammatory response. Keeping on the LPS theme, we can measure LPS binding protein, or LBP. The job of LBP is to bind and to present LPS to additional components of the immune system for targeting and elimination. We can also measure intestinal fatty acid binding protein. It is an intracellular protein specific to intestinal epithelial cells, and when they are damaged, it gets released into the plasma. We can also measure peptidoglycan, which similarly to LPS is a primary component of the cell wall in most bacteria. Or we can use sugars of different sizes, the most popular being the lactulose-mannitol ratio, which calculate permeability depending on the rates of passage into the urine. It's with this acute or chronic passage of gut compounds into the body systemically which drives so many problems. How else do you think all of this E. coli DNA makes its way into these brains shown here in Figure C? Both in the gray matter and white matter of Alzheimer's brains is significantly more E. coli DNA as compared to the healthy controls. Now you may say, wait a second, if they are healthy controls, why do they have E. coli DNA in their brains? Well, as you'll see in further slides, it's normal to have gut permeability and gut compounds in the body systemically. The keys are the following. 1, the quantity. 2, the composition. And 3, how your immune system will respond. Will it respond efficiently and with tolerance, or will it respond in a hypervigilant manner? Much like with COVID, right? Those who had a cytokine storm did not fare as well as those who had a more tolerant and efficient response. In fact, we can all have gut permeability from everyday stressors. This is an experiment to help understand the connection between emotional stress, the microbiome, and disease. In this study, the goal was to get couples arguing over marital hot topics. During these visits, a number of blood markers were taken. You can see in Figure A, we're talking about one of those permeability markers I mentioned earlier, LPS binding protein. The researchers found that those participants with the more hostile marital interactions had higher LBP than those who were less hostile. In other words, whole or parts of bacteria, as measured indirectly by LBP, have escaped the gut and gotten into circulation. LBP is the body's response to this escape. So what the study is demonstrating is that for those who fought most aggressively over marital hot topics, they produced the most stress hormones, which then went on to do a number of things, one of which was increased gut permeability, releasing LPS into circulation, which is something I always talk about as a bad thing. Here's another type of short-term everyday stressor. Here we have a public speaking paper. Here they too measured gut permeability, but this time with the lactulose-mannitol urinary excretion test. As you can see in Figure 2, an NSAID, which is known to cause permeability, and public speech, both significantly increased gut permeability in these subjects. Salivary cortisol was only increased after public speech, and the effect of public speech on permeability was only present in subjects with a significant elevation of cortisol. In other words, those most stressed out. Now understand that in this paper and the previous paper, gut permeability was mediated by the immune system triggered by the stress response. except for the NSAIDs. And this was proven in the paper with the use of a mast cell stabilizer. Even eating can cause a temporary increase in gut permeability. That's right, eating. There is proof that a high-fat diet, especially high in saturated fats, has been found to cause dysbiosis, inflammation, and LPS translocation into the body. Spikes in LPS, aka endotoxin, in the blood have been seen in multiple studies following a high-fat meal in healthy subjects. There's enough evidence to show that the process of absorbing a high-fat load is damaging to the cells that line our gut. The increased requirement for the chylomicron-led absorption of lipids distends intercellular space during the process, which seems to loosen the bonds between the enterocytes. And although this is a temporary event, it allows quantities of LPS to enter circulation. And the key culprits for this inflammation and destruction are long-chain fatty acids. But what we're really talking about are not these short-term events. We're talking about dysbiosis in the gut. When the bad guys are in charge, it is the chronic environment that sets us up for most of our problems. That's what we'll spend the rest of this video covering. To reinforce this constant theme across many conditions, let's start with gut permeability, aka leaky gut, and autoimmune disease. What do the trials have to say, and what do these dysbiotic pictures have in common? We start with a lupus paper. Here, these authors cite the connection between gut permeability and bacteria or parts of bacteria entering circulation, something I mention about every video. And here, they talk about how dysbiosis leads to a hypervigilant immune system with a breakdown of immune tolerance to your very own cells. See my videos on autoimmune disease for more. Up in Figure 1, they cite increased levels of some of the usual opportunistic pathogens I mentioned, such as Streptococcus, Veillonella, and R. navis, as problematic in lupus. And below that, the passage of bacterial components such as LPS into the bloodstream, which can confuse the immune system and cause antibody production against your own tissue. Here we have a biopsy paper investigating ankylosing spondylitis. They state, quote, adherent and invasive bacteria were observed in the gut of patients with AS, with the bacterial scores significantly correlated with gut inflammation. Now let's see their results. In chart N, we see significantly more E. coli in AS subjects as compared to healthy control. Now remember, this is a biopsy paper, so these results are from the cells which line the ileum, not the feces. These are bacteria which have adhered to and invaded the cells. With this pathogenesis, zonulin levels, as seen in G, are much higher in AS subjects, especially AS chronic, as compared to healthy controls. Remember, zonulin is that thing that our bodies secrete in response to a challenge in the gut, which causes the cells which line the gut to separate. And we see that all of these factors of gut integrity, cadherin, JAM, claudins, and zonular occludens, are significantly reduced in AS. These are all great examples of the connection between dysbiosis, gut permeability, and diseases, in this case, AS. And in this study, they used the lactulose-mannitol ratio to assess gut permeability in type 1 diabetes. That's the autoimmune version, not type 2. And what they found was, quote, all groups of subjects with islet autoimmunity showed an increase in intestinal permeability. They say repetition is key for learning, and so I have more of that for you here. Once again, we'll highlight the connection between gut permeability and a given disease, in this case, Hashimoto's. In this study, the researchers compared the plasma zonulin levels of 77 patients to age-matched healthy controls. What did they find? Would you be surprised if I told you that the serum zonulin levels, which you now know is a marker for gut permeability, were significantly higher in those with Hashimoto's as compared to the healthy controls? Again, this is explained by gut microbial dysbiosis, which not only drives permeability, but also an inappropriate immune response, one that is overreactive, one that has very little tolerance for discriminating between which signals are from a true enemy and which are from self, and thus all can suffer from an unregulated attack. Let's wrap up this subsection with some quotes from this systemic review, which included 26 papers looking into the association between the gut microbiota and type 1 diabetes. It's a good summary of this topic. You'll just hear it from the 8 authors of this paper. Quote, In patients with type 1 diabetes, some bacteria increase mucin degradation, results in reduced integrity and increased permeability of intestinal mucosa that leads to bacterial penetration. The penetration of bacteria into the intestinal mucosa leads to the stimulation of the immune system and production of antibodies against them. Cross-reaction of these antibodies and surface antigens of pancreatic beta cells, as well as T cell cross-reactivity, results in the destruction of beta cells and the formation of type 1 diabetes. Butyrate is one of the most important byproducts of microbiota metabolism and plays an important role in colonic Treg induction, down-regulation of pro-inflammatory macrophages, and integrity enhancement of gut barriers through increasing mucin production. Zonulin is a protein that can be assumed as an important indicator of mucosal integrity and gut permeability. This protein modulates intercellular junctions and macromolecular passage through them. Some bacterial groups can alter mucosal integrity by affecting zonulin. Increase in Bacteroides species and Veillonella species, or decrease in Faecalibacterium species and Roseburia species, correlates with increased serum zonulin levels in type 1 diabetes. And our last quote, gut microbiota ingests and ferments fibers and produce short-chain fatty acids. Short-chain fatty acids enter the blood circulation and modulate Treg differentiation, thus autoimmunity is prevented. Now let's take a look at the key taxa in autoimmune diseases across the board in my now familiar chart. We're going to do this for a number of conditions to reinforce the generally same taxa at play. Here we see the classic health promoters, Allostypes, Carpococcus, F. Prozitzii, Lachnospira, and Roseburia, significantly reduced, whereas we see classic opportunistic pathogens such as Eggerichella, Enterococcus, E. coli, Klebsiella, R. navis, Streptococcus, and Veillonella significantly increased across the board in autoimmune diseases. And here is your so-called probiotic Lactobacillus, which people keep writing me insisting that it can't be bad, with mostly negative data shown here. It's not as bad as the true opportunistic pathogens, but it's nothing compared to the health promoters. Is there dysbiosis and gut permeability in COVID? Hell yeah, there is. In this slide, we show the results of a study which looked at 3 plasma markers of intestinal permeability in COVID subjects versus healthy controls. In figure A, you see fatty acid binding protein. As you can see, this marker of intestinal wall damage is significantly higher in the COVID subjects. Figure B highlights peptidoglycan, which we covered how it signifies bacterial intrusion from the gut to the body systemically. As you can see, it's also significantly increased in COVID. And in figure C, we see LPS. Again, the serum marker of systemic bacterial burden is significantly higher in COVID. Both peptidoglycan and lipopolysaccharide are referred to as pathogen-associated molecular patterns. That's a fancy way of saying that the immune system recognizes these chemical signatures, sounds an alarm that signals invader, causing a mobilization of the defenses. Although a necessary part of survival, high levels or long durations of immune system-induced inflammation is not a good thing. And for our second and last COVID paper, we see our now familiar marker, zonulin. In figure B, you can see how moderate and severe COVID subjects had significantly higher levels of zonulin in their plasma versus healthy controls and mildly affected subjects. Now let's take a look at the microbial fingerprint for COVID. Here we see the classic health promoters, Anaerostypes, Carpococcus, Eubacterium, F. Prozitzii, Lachnospira, Roseburia, and Ruminococcus, significantly reduced, whereas we see classic opportunistic pathogens such as Enterococcus and Streptococcus significantly increased across the board in COVID. And here is your so-called probiotic Lactobacillus with mostly negative data. Here we have plasma LPS levels in perspective. For Alzheimer's, plasma LPS levels are equal to those in liver cirrhosis. That's not a good thing. And just below HIV/AIDS, also a scary thought. Here they have LPS levels for healthy humans at 1/6 the amount. Healthy people do have LPS in their serum. It's just far less than those who are dysbiotic. It's the chronic increase in level and type of bacteria that drives inflammation, which is at the core of so much disease. Just a brief pause here in the presentation. If you could just hit like and subscribe, it would really help this channel out. In our second and last dementia reference, we have 89 older persons with cognitive performance from normal to dementia underwent a PET scan and blood analysis. Not surprising, they showed that neurologic inflammation was in every case correlated to LPS and butyrate. The more LPS, the higher the inflammatory signal. The more butyrate, the lower the inflammatory signal. And what does the microbial fingerprint show for dementia? Well, we see some of our usual butyrate-producing health promoters significantly decreased. E. rectile, F. Prozitzii, Roseburia, and Ruminococcus. While we see the classic opportunistic pathogens, E. coli, significantly increase in dementia. And here is your so-called probiotic lactobacillus with all negative data points. And is there gut permeability and anxiety and depression? You bet. Here we have a paper which includes a number of characteristics seen repeatedly in the literature. Although they didn't analyze the microbiome, we can tell that there was dysbiosis. How? First, we see that levels of serum butyrate, serum is a better marker than fecal butyrate, are significantly higher in the healthy controls versus those with depression. Also, as I always say, I want to increase the butyrate producers. They determine the health of the microbiome. Secondly, we see significantly higher levels of toll-like receptor 4, TLR4, expression. TLR4 is a component of the immune system responsible for recognition and alarm in response to LPS, that common pro-inflammatory component of many, but not all, bad-acting bacteria. Because of this dysbiosis, we see increased gut permeability, literally with these tissue samples. And to the left of them, we see significant reductions in 3 of the proteins we saw earlier responsible for maintaining the gut barrier. Because of this, we see significant increases in inflammation. High sensitivity CRP is a systemic, nonspecific marker for inflammation. It is significantly increased in those with depression as compared to healthy controls. Also, we see NF-kappa beta, another key component of the immune inflammatory response, also increased in depression. Here we have an alcohol dependency study. CT equals control. AD high IP is alcohol dependency with high intestinal permeability, and AD low is alcohol dependency with low intestinal permeability. As you can see, alcohol dependency subjects with high permeability had a drastic decrease in the abundance of Ruminococcus, Faecalibacterium, Subdolly granulum, Acilibacter, and Aerophyllum. As a result of this dysbiosis and permeability, the alcohol-dependent subjects with high permeability were still characterized by higher levels of depression, anxiety, and craving, reinforcing the inflammatory connection between the gut and the brain. And how about the microbial fingerprint for anxiety and depression? Again, we see those familiar butyrate-producing, antibiotic, and oxygen-sensitive health promoters significantly reduced in the microbiomes of those with anxiety and or depression. Familiar names like Coprococcus, F. Prozitzii, Roseburia, and Ruminococcus. While the familiar opportunistic pathogens, which are significantly lower in healthy controls as compared to those with anxiety and depression, are Haemophila, E. coli, and Streptococcus. Lactobacillus is equally weighted between positive and negative data points here. How about type 2 diabetes? Any leaky gut here? Yep. Here we have a study with 90 subjects with type 2 diabetes as compared to 28 healthy controls. This study measured serum LPS, zonulin, and fatty acid binding protein. All measures of gut permeability. Therefore, all measures of gut dysbiosis, an unhealthy balance of bacteria in your gut. Not only were there significant differences between the healthy controls and the diabetes subjects as seen in Table 2, but those with more severe blood sugar abnormalities, as measured by hemoglobin A1C, had more gut permeability. And in this type 2 diabetes study, we can see in Figure 2 significantly higher zonulin levels as compared to healthy controls. Again, normal controls have detectable zonulin levels too, just significantly lower than those with type 2 diabetes. This increase in intestinal permeability results in significantly higher levels of LPS, due to more LPS in total in the gut and more release into the blood. Again, healthy controls have detectable serum LPS levels. They are just significantly lower than those with type 2 diabetes. This elevation in LPS causes an increase in inflammation, as shown here in B. I talk about TNF-alpha a bit. It's a good marker for inflammation, which is why it's used here. And again, you can see how healthy controls had detectable serum levels, just significantly lower than those with type 2 diabetes. LPS reduces muscle insulin sensitivity for one. It also damages insulin production. It also reduces serum HDL, as HDL plays a key role in its disposal. LPS also results in increased triglyceride levels. When we look at the microbial fingerprint for type 2 diabetes, we see the same themes in general. Our butyrate-producing health promoters, such as Anerostipes, Eubacterium, F. prausnitzii, and Roseburia, are significantly reduced in the average microbial fingerprint for those with type 2 diabetes, while the classic opportunistic pathogen, E. coli, is significantly increased. And the taxon with the most data points is your so-called probiotic, Lactobacillus, with a horrific data profile. In this Parkinson's study, we see significantly higher serum zonulin levels in the Parkinson's group as compared to the controls. Like all these papers, I'm showing you just one of several with the same results. And as always, once I compile all the data points from my meta-analysis, I get this chart here. Again, in the average Parkinson's microbiome, we see that the healthy controls consistently have significantly more health promoters, such as Carpococcus, F. prausnitzii, Roseburia, and Ruminococcus, as compared to those with Parkinson's, while they have significantly more classic opportunistic pathogens, such as Enterococcus, E. coli, and Streptococcus. And here is Lactobacillus. And how about an IBS, which is a clear state of dysbiosis? Again, we see increased serum zonulin levels in both IBS constipation and diarrhea. The authors go on to state, quote, in our patients with diarrhea-predominant IBS, the increase in permeability was clinically relevant as serum zonulin levels correlated with diarrhea severity. And when I compile all the data from the 54 studies I used for my IBS meta-analysis, we get this chart here. What you see here is the average microbiome profile for IBS. And again, we see key health promoters such as Allosticps, F. prausnitzii, and Roseburia, among others, significantly reduced in the IBS microbiome, while the classic opportunistic pathogens, Egrithella, E. coli, R. navis, Streptococcus, and Veillonella, are significantly increased. Again, here is your Lactobacillus. In an IBD, which is Crohn's disease and ulcerative colitis, which is an extreme case of dysbiosis, we see the same. From this paper of 118 IBD patients as compared to 23 healthy controls, we once again see a significant increase in gut permeability as measured by serum zonulin. And what do you think? Is a similar dysbiotic microbial fingerprint in IBD responsible for this increase in intestinal permeability, like in all the others we've seen thus far? Yeah, it is. If we first look at Crohn's subjects, we see significant reductions in Allosticps, Anerostipes, Carpococcus, Eubacterium, E. rectale, F. prausnitzii, Roseburia, and Ruminococcus, among others, while they have significant increases in our now very familiar opportunistic pathogens, Enterococcus, E. coli, R. navis, Streptococcus, and Veillonella. And I know you'll find this shocking, but here's some terrible data points for Lactobacillus and Crohn's. And what do you think? Will we find more incredible consistency across the board for ulcerative colitis, the other member of IBD? Of course we will. We see in the same main players over and over, with additional members completing the microbial fingerprint for each condition. Once again, Allosticps, Carpococcus, Eubacterium, E. rectale, F. prausnitzii, Lactospira, Roseburia, and Ruminococcus, among others, are significantly reduced in the UC microbiome, while Enterococcus, E. coli, R. navis, Streptococcus, and Veillonella are significantly increased. And once again, we see Lactobacillus with ugly data points in the ulcerative colitis microbiome. How about for liver health, which is a video I'll be launching in the near future? I've combined data points for both non-alcoholic fatty liver disease and NASH. Not only in Table 3 do we see significant increases in gut permeability and liver diseases compared to healthy controls, as measured by plasma zonulin, but we also see far higher permeability as the severity of liver disease increases, which is logical. And which microbial taxa are contributing to this gut inflammation-driven permeability? Well, it would be a lack of good bacteria keeping the gut lining intact and an overabundance of bad actors driving permeability via an immune system response. Any guesses as to which names we'll see and to which cohort they belong? You guessed it. Those with non-alcoholic fatty liver disease and NASH have significant reductions in the butyrate-producing, oxygen and antibiotic-sensitive taxa, Anerostipes, Coprococcus, Eubacterium, Lactospira, F. rosacei, Roseburia, and Ruminococcus, among others, while they have significant increases in the classic opportunistic pathogens E. coli, Klebsiella, Streptococcus, and Bayonella. And I added Lactobacillus to the end, not because I consider it part of the fingerprint, but just for your own reference. The data isn't pretty here once again. So why in the world would you insist on taking Lactobacillus probiotics for any given condition when you've seen all the data I presented here in respect to gut permeability and microbial fingerprints? It makes absolutely no sense. Why not aim to increase the abundance of the health promoters who have unquestionably amazing data points? And this is no coincidence. This is remarkably consistent, and it makes sense. These bacteria are proven health promoters, while the bad guys with the ugly data points are proven opportunistic pathogens. In time, I'll launch a video on hormones and female health, with a focus on PCOS and endometriosis. Do you think there's permeability here too? Well, here we have a PCOS study which shows just that. And metabolic syndrome is highly correlated with PCOS. And we already saw earlier that there's dysbiosis and gut permeability in type 2 diabetes. Well, here you can see clear correlations for measures of the number of menstrual cycles with adiposity, insulin resistance, insulin sensitivity, and zonulin. Here we see an inverse correlation. The more zonulin, the fewer menstrual cycles. So we see a clear correlation between menstrual dysfunction and gut permeability. And for our second and last permeability study of PCOS, in Figure 2, you can see a clear trend in what's called an M value on the y-axis, which is a measure of insulin sensitivity, and LBP on the x-axis, which, if you recall, is LPS binding protein, which is an indirect measure of serum LPS, which itself is an indirect measure of gut permeability. So the more LBP, the more LPS, which means more LPS is escaping from the gut. And note, the LBP numbers were not only significantly higher in those with PCOS who were lean versus healthy control, but it worsened with increasing weight. The hormone imbalance in PCOS does not occur in a vacuum. And if you read the text in the box, you'll see how the authors connect diet, microbiome, inflammation, insulin signaling, and PCOS all together. As I always say, it's all connected. You don't just get PCOS or dementia or rheumatoid arthritis out of nowhere. In a couple of my videos to date, I've discussed dysbiosis and autism, and in time, I will launch a video dedicated to this topic. And not surprisingly, we also find gut permeability in autism, as shown in Figure 1, as measured by the lactulose-mannitol ratio. In my video on fecal microbiota transfer, I bring up autism a couple times. If you want more perspective, you can watch that as well. When these researchers put the autism subjects on a gluten and casein-free diet, their gut permeability plummeted to below the controls, even as shown here in Figure 2. Now, a couple of things. I'm sure if you're the parent of an autistic child, you've already tried a gluten and casein-free diet, maybe with some success, maybe with very little, if any. But it's a start. However, it's not addressing the root cause of the microbiome. The inflammatory response to these dietary proteins is due to the dysregulation in the gut. We have to address the dysregulation, which is to say, the dysbiosis driving the dysregulation. And for our last slide emphasizing gut permeability and disease, I could have added more, we have this meta-analysis of 13 research papers. Various markers of intestinal permeability were compiled from these studies. And whether it was LPS, zonulin, LPS binding protein, intestinal fatty acid binding protein, or other measures we haven't discussed, those with cardiovascular disease consistently had significantly more permeability as compared to the healthy controls when they were grouped together, as shown in Figure 2. And LPS and zonulin were also significantly higher individually. I'll soon be releasing a video on cardiovascular disease and the microbiome. Be sure to watch that. So let's put this dysbiosis gut permeability disease picture together in one slide. I frequently say that antibiotics are terrible for the microbiome. Watch that video for much more specific information. If we look at the first column here, it lists all the bad guys shown to be increased by antibiotics in multiple studies. Column 2 lists the bad guys shown to be significantly increased in multiple PPI studies. That looks like column 1, no? The names from columns 1 and 2 should be very familiar to you by now, because we've mentioned them time and time again in this video. And just to refresh your memory, in column 3, I listed the ones from this presentation which had overlap with columns 1 and 2. Of course, there are other opportunistic pathogens, but these listed here overlap with the bulk of the antibiotics and PPI data. Nobody else has done all this work. With these names in mind, let's look at our final slide. In the C. diff infection, by the way, the number one risk factor is excessive antibiotic use. Do you think there will be any similarities between what antibiotics do to the microbiome and all the rest of the data we've seen in this video? Here's the microbial fingerprint for C. diff, which is dysbiosis in the extreme. This comes from my comprehensive meta-analysis of all relevant papers I could find. Once again, we see significant reductions in the health promoters, allostypes, Carpococcus, Eubacterium, F. prausnitzii, Roseburia, and Ruminococcus, among others. While many of the classic opportunistic pathogens are significantly elevated in the C. diff gut, to include Enterococcus, E. coli, Klebsiella, and Payanella. And yes, once again, in the extreme case of dysbiosis no less, the quote-unquote probiotic Lactobacillus has terrible data points. 100% of the time, when a significant difference was found for a human fecal microbiome original research paper, Lactobacillus was significantly higher in the C. diff infection subjects as compared to the healthy controls. I hope I made my point. Please, no more comments on YouTube questioning where I'm coming from in regards to Lactobacillus. But I don't want the theme of this presentation to be bashing Lactobacillus. I want you to walk away with the knowledge that it is this incredible consistent microbial fingerprints which drive intestinal permeability. Now you can understand my statement when I say I can tie dysbiosis to just about every disease condition you can think of. We have two worlds within us. There's within the gut, and then there's outside the gut. These two worlds are connected by intestinal permeability. It's fairly easy for the average person to grasp the idea that a bad diet and antibiotics are changing their gut microbiome for the worse, and this can result in diarrhea, constipation, Crohn's disease, colorectal cancer, or ulcerative colitis. But it's not so easy to grasp the connection between your dysbiosis and Parkinson's disease, dementia, depression, anxiety, autoimmune disease, and the list goes on. This is why I made this presentation. It is this chronic level of inflammation that drives these conditions. The excessive escape from the gut of whole bacteria, parts of bacteria, and food peptides in quantities higher and in worse composition than would otherwise be the case in those who are healthy. It is then the dysregulated chronic immune response to the various triggers which drives our collective disease in large part. Therefore, the root cause is not an anti-inflammatory drug. The root cause is addressing the dysbiosis. Whether your health concern is within the gut or outside the gut, mediated by gut permeability. Well, I hope you enjoyed that video, and I will say that basically every single day on my YouTube comments and in emails, I get a lot of thanks from people out there who really appreciate the information I've been sharing. And so part of that is you're welcome. The other part is you can contribute by clicking on the super thanks below. And if you're not doing a consultation with me and you're not purchasing any protocols, it's a great way to support this channel. Each presentation, depending on the presentation, but most of them take an incredible amount of time to put together. There's a lot of material. There's a lot of data checking. And so it's just sometimes 50, 60, 70 hours to put together one presentation. And so if you can just click that super thanks, I'd appreciate that, and we'll keep the information coming.